Solubility equilibrium. So solubility equilibrium, we're going to look at the solubility product concept. What is solubility? Solubility is how well something will dissolve in water. So if something dissolves a lot or completely in a liquid, it's very soluble. If it doesn't dissolve much, it's not soluble. So this product, this constant, will tell us how soluble an ionic compound is in water. The smaller KSP is, the lower the solubility is. The higher, the greater the solubility is. So here's some product constants. Here we have the solid salts, and this is how soluble they are in water. So you can see that of the halide, probably the most soluble here is lead chloride. The least soluble is silver iodide. The smaller the number, the less soluble, the less it dissolves in water. Here is the general equation to find the solubility product. Now this really looks familiar. It looks like K equilibrium. So it looks just like this equilibrium constant equation. And that's actually where you get it. But the thing is, if we had A plus B goes to C plus D, we're looking at the solubility of a solid compound. So a solid salt. So that would be maybe something like this. That's solid. But remember, when we talk about equilibrium, we don't care about the solids or the liquids. We only care about gases and aqueous solutions. So this goes away. We're left with one, and we're left with this. So here we have this equation for this reaction. Again, we don't care about this because it's a solid. Now let's try some of this out. We're going to determine the concentration of silver and chloride ions in a saturated silver chloride solution. Solubility product constant of AgCl is 1.8 times 10 to the minus 10. So let's write this reaction. We have silver chloride, a solid, goes to silver plus chlorine. Chlorine has a charge of -1, so it's a 1-to-1 ratio here. Silver would have also a charge of +1. So we have 1.8 times 10 to the minus 10 equals concentration of silver multiplied by the concentration of chlorine. So since those concentrations are going to be equal, we can substitute the chlorine for another silver to figure this out. Because before, if we had two unknowns, we wouldn't be able to figure this out. So we can equal those as the same concentration. So then we have 1.8 times 10 to the minus 10 equals Ag plus squared. And then we solve by taking the square root of 1.8 times 10 to the minus 10. We had a concentration for silver of 1.3 times 10 to the minus 5 moles per liter. That will also, since they are equal, be the concentration of chlorine. So this is a concentration of both the silver and the chlorine. What happens if you add an ion that is similar to one of the ions already there? You get the common ion effect. So we have this lad here, and he just loves eating bananas for breakfast. And he will eat a lot of bananas. Now a banana, full banana, will break down into a banana and peel. So that's basically soluble. It breaks down banana and peel. So he will break it down into the banana and peel. So if we have 3 bananas here, he will then break down it into 3 bananas and banana peels. So 3 bananas, 3 peels, it's soluble. He breaks it down because he wants to eat those bananas by itself. What if we introduce banana slices for breakfast? Well, that's the same thing, really. It's common to the banana inside. So that's a common ion because that's common to the banana inside. So he will eat those banana slices as well as some of the bananas inside. But the thing is, he's not going to want to eat so many of those bananas inside the peel now because he already has those banana slices. He's not going to break down those full bananas out of the peel because he already has some of those common banana slices getting in the way. It doesn't need to break it down. So let's say he'll only break down one banana, and so he'll get one banana and peel, plus he'll eat those slices. So the common ion effect, those common ions will get in the way of breaking down the original compound. Because why would he peel more bananas if he already had banana slices? So he doesn't need to break those full bananas down in order to eat banana. So the common ion effect is when you get a decreased solubility of a substance caused by addition of a common ion. For example, if we look at silver chloride going to a silver ion plus a chlorine ion, the KSP is 1.8 times 10 to the minus 10. If we add silver nitrate to the above solution, what will happen? Now the common ion is silver. It means we're adding more product here, more silver. Looking at Le Chatelier's principle, we can see the shift. That means what happens if we add more product here, it's going to shift to the left, which means more sodium chloride or silver chloride would stay intact. It's basically, let's say if you're just trying to dissolve some salt in some water, keep adding salt, you're going to stop dissolving the salt. The salt's going to remain a big lump. So we've all dissolved some sugar or some salt, and we're talking ions here, so we'll look at table salt. If we dissolve some table salt in water, we add some, it will dissolve. But if we keep adding salt, it will stay in a solid form. It will not dissolve. If we add the same, even though it's a different salt, we have a common ion here, shift to the left, and the silver chloride would stay intact. Finding the equilibrium ion concentration in the presence of a common ion. So the KSP of silver iodide, which is AgI, is 8.3 times 10 to the minus 17th. What is the iodide ion concentration of a 1 liter saturated solution of AgI to which 0.02 mole of AgNO3 is added? So when we break this up, get this, we want to know what is the iodide ion concentration of a 1 liter saturated solution of AgI to which 0.020 moles of silver nitrate is added. So we are adding silver nitrate, means we have a common ion in silver there. That's going to affect equilibrium. It will shift it to the left. What is the iodide ion concentration going to be? First, we write this equation out so we can see what's going on. Then we write the solubility expression. KSP equals silver concentration times the concentration of iodide ion. That equals 8.3 times 10 to the minus 17. So just like just finding KSP, let's assume that I is X. And also silver is X. But we're going to assume that X, since we're adding 0.02 moles, X will be 0.020. Now why is it 0.020 and we have the same value of 8.3 times 10 to the minus 17? Well, remember Le Chatelier's principle, it will shift back to whatever it can do to get back to this equilibrium, this solubility product. Now, so all we have to do is multiply this together. But if this is going to be the same as before, we're going to assume that this X is extremely small. So if this is extremely small compared to 0.02, in order to get such a small number here, we can make that assumption and get rid of this X. Then we will just have 0.02. Then we can multiply those two together and solve for the concentration of iodine. So we can multiply those together now, based on that assumption, and we can say X, which is iodine concentration, is equal to 8.3 times 10 to the minus 7, and then X, we solve for X, that is equal to 4.2 times 10 to the minus 15th. So the equilibrium concentration of the iodine ion is 4.2 times 10 to the minus 15. Okay, let's try this one. The KSP of strontium sulfate is 3.2 times 10 to the minus 7. What is the equilibrium concentration of the sulfate ion in a 1 liter solution of strontium sulfate to which 0.1 mole of strontium acetate has been added? So we see here we have a common ion, strontium. We want to know what the concentration of the sulfate ion is if we add strontium acetate. So first we're going to write out the equation. So we have strontium sulfate. Equilibrium will go to strontium plus sulfate. Sulfate is 2 minus, that will be 2 plus. Now at equilibrium, we have strontium is equal to sulfate. Okay, so that's at equilibrium, those concentrations will be the same. So then we can write the KSP is equal to the concentration of strontium multiplied concentration of sulfate is equal to 3.2 times 10 to the minus 7. So SO4, we're going to say, that's sulfate, we're going to say that's X. Now this was also X, but we added 0.1 mole to it plus 0.1 mole. But this X, we don't want some crazy quadratic here, so this X here is going to be incredibly small, since this is small. So we can get rid of this. We're going to make the assumption that it's incredibly small. So we will have this, which comes out to be 0.1 x equals 3.2 times 10 to the minus 7. We solve for x, and we get 3.2 times 10 to the minus 6. This is the concentration of the sulfate ion at equilibrium if we add 0.1 mole of strontium acetate to it.